All right, we are taking a look at an example here where we're dealing with a limiting reactant. Now, if you remember limiting reactant, what that means is that when we put our chemicals into the container to start with and a reaction takes place, one of our substances will get completely used up. And at that point, when that reactant is completely used up, the reaction just stops. It doesn't happen anymore. We can't make any more product. And so we typically call the reactant that gets used up completely, we call it the limiting reactant, or sometimes we use the term limiting reagent. What we're going to do is look at how we solve a stoichiometry problem involving a limiting reactant. And so to do this, just like any stoichiometry problem, we're going to need to work with moles, right? That's how we relate one substance to another. We want to be able to identify what the limiting reactant is and use it to determine how much product will get made. So in this question, it says if 92 grams of sodium and 196 grams of phosphoric acid are placed in a reaction vessel, determine the mass of hydrogen gas that can be produced. The unbalanced reaction is shown below. So remember, with any stoichiometry problem, the first thing we need to actually do is balance the chemical equation. So let's balance this. If we take a look right now, one of the biggest things we're going to have to deal with is balancing the hydrogens. I need to balance my hydrogens by putting a 2 there and a 3 there. Okay. Now I can work through the rest. I need to balance the phosphate. I've got 2 phosphates on this side, so I'm going to need a 2 in front of my sodium phosphate. And now I've got 6 sodiums on the product side, so I need a 6 coefficient in front of the sodium. So we've got our balanced equation, and now as we do with any problem, we're going to write down what we have. We know the mass of H3PO4 is 196 grams. And we're going to need a molar mass because to get from mass to moles, it's all about molar mass. So if we solve for the molar mass, we're going to get 98 grams per mole. So that's 3 hydrogens, 1 phosphorus, and 4 oxygens. Look at your periodic table, find the masses, and add those together. So that'll allow us to find moles of the H3PO4, the phosphoric acid. We also have in our question 92 grams of sodium. So our mass of sodium, we know. And the molar mass of sodium we can get from our periodic table as well. And we know that's 22.99 grams per mole. So that'll allow us to find moles of sodium. Then we're going to have to use those to figure out which is going to produce the lowest number of moles of hydrogen, right? The one that produces the lowest number of moles of hydrogen, that's the limiting reactant. And once we know that, we can use the molar mass of hydrogen, which is 2.02 grams per mole. Because remember, there's 2 hydrogen atoms per H2. And that'll allow us to find the mass of hydrogen, right? So the biggest thing we have to recognize is we're going to have to figure out which of these 2 reactants runs out first, which one is going to be used up first. So that's what we're going to do. Now to tackle this problem, I like to sort of work with one reactant at a time and figure out how much product would get produced from that reactant. So let's start with the phosphoric acid. So I'm going to sort of just keep track here. So moles, remember, we are going to find moles. So if we're sort of keeping track, we can get our moles using the mass and the molar mass. That's the first thing we're going to do. And then we're going to connect this with a mole ratio, right, as our second thing to do to figure out moles of hydrogen, right? That'll allow us to figure out moles of hydrogen based on using up all the phosphoric acid. The other thing we're going to have to do is figure out moles of sodium. And once we've got that, we want to do a mole ratio to figure out the moles of hydrogen, right? Then we compare the moles, whichever produces less hydrogen, that's the one we'll then calculate the mass with. So the last thing we'll do is we will calculate the mass using the moles and the molar mass. Using that lower amount of hydrogen that we produce, right? So that's our plan here. So we're going to find our moles of H3PO4. We're going to do that by taking the mass and dividing by molar mass. So we know 196 grams divided by 98 grams per mole, which would give us a value of 2 moles. So that's our number of moles of H3PO4. Once we've got that moles, now we're going to do our mole ratio. So our mole ratio, we're going to figure out the moles of hydrogen. And we know that's going to be the moles of H3PO4 times the ratio that we find in our balanced chemical equation. So we'll notice the one we want to find is on top. So 3 moles H2 divided by 2 moles of H3PO4. So those numbers, the 2 and the 3, are coming from our balanced chemical equation. They're the coefficients, right? The mole ratio step is where those coefficients get involved. So I take my 2 moles of H3PO4 and I'm going to multiply by 3 over 2. And that will give me a value of 3 moles. So that means if all the H3PO4 gets used up, I can generate 3 moles of hydrogen gas. Right? So we figured out how many moles from the hydrogen gas. Now let's work with the sodium. If we work with the sodium and assume that all the sodium gets used up, we're going to try and figure out how much hydrogen that would make. So let's figure out our moles of sodium. That again is mass divided by molar mass, which in this case is 92 grams divided by 22.99 grams per mole. And we are going to, just going to try and fit this in for us. Probably squeeze it in there. When we solve that, our number of moles of sodium is going to be equal to 4.00173 moles. So that's our moles of sodium. Now, we've got how much sodium we have. If all that sodium gets used up, now we need to figure out how much hydrogen we would make. So we're going to take our number of moles of sodium and multiply by the mole ratio in our balanced chemical equation. Again, we want to find hydrogen, so hydrogen's going on top. And sodium is what we're working with, so we're going to get rid of the sodium. It's going to be on the bottom. So we take our 4.00173 moles and multiply by 3 over 6, which is really just dividing by 2. And we would get 2.008699 moles. So there's our moles of hydrogen. So now this is the point where we look and say, okay, which substance, H3PO4, or sodium, which of those two substances produces the lower number of moles of hydrogen? And in this case, our sodium only produced 2 moles of hydrogen versus our H3PO4 producing 3 moles of hydrogen. So what that means is our sodium is going to run out as soon as we produce 2.0008699 moles of hydrogen. Once that happens, the reaction stops. We'll never be able to make 3 moles of hydrogen with what we put in the container. So we know from here that since, this is my short form for since sodium generates less moles, of hydrogen, it is the limiting reactant. Right? So if we know that it's the limiting reactant, then we know this is what we have to use to find the mass of hydrogen. So when we do this to find the mass of hydrogen, we're going to work with the moles of hydrogen times the molar mass, right? That's our calculation. So we're going to take this value of 2.00. We're going to take this one right here. Right? We're going to plug that in because it was limiting. The sodium's limiting, so that's how many moles of hydrogen we can make using all the sodium. And then we're going to multiply by the molar mass, which is 2.02 grams per mole. So our mass of hydrogen that we can actually produce would be 4.04 grams, rounded to 3 significant digits based on the initial mass that we had. So we've figured out our theoretical yield, and so we can finish it off with a statement. We're going to produce 4.04 grams as our theoretical yield, right? So this type of problem involves a number of steps, right? And the key is to recognize which reactant is going to give us the path that produces the lowest amount of product. Because once we reach that quantity of product produced, the reaction would stop. That's the idea of our limiting reactant. And we're able to figure out what our theoretical yield would be.